What I shall present today is a completely new version of an old program which was called Geometrica. And the spirit of this new version did not change. And it consists of having an introduction to geometry through three main aspects: the Cartesian or analytic aspect, which is now very important in Mathematica itself with the concept of regions, the Euclidean approach, and the differential geometry. And what is really new in that version is special functions which help for making demonstration, and also functions inside the code which are interactive. And this is what I shall talk about. To help animating some scene, there are two special which have been created. One is arc, which gives the element of an arc, of curve, of any curve, and strip, which is an element, a patch if you like, of a surface which can be expanded at will. So in the first example, I shall show you an application of arc to a special swing. So the example I shall give you for this special swing is the following. If you take a parabola and a similar parabola which rolls on the first one, the locus of the tip of the parabola, of the moving parabola, describes, thank you, describes a so-called cissoid. And I shall show you how to do that. First, the parabola is a conic, and it has C before because it's Cartesian conic. And here the equation is y squared equal to x. And a conic is defined by six coordinates, a line by 3 coordinates, a point by 2 or 3 coordinates, and a quadric, I shall show that before, by 10 coordinates. And the rolling of the moving parabola is defined by the symmetry of the fixed parabola with respect to a tangent to a moving point on the parabola. So the tangent is defined here as a special line. And O is the tip of the parabola, the fixed parabola. And this is now the expression as a parametric point. And the parametric point is a representation of that parametric curve, but it is different from Mathematica. Each coordinate is a pure function. And the third argument defines the range of variation of the parameter. So before doing the animation, you see that the rolling parabola will span a space around the fixed parabola, and that you have to fix before in order to have a stable animation. Now we can code its, let's say the manipulate is just a repetition of what I did before for a moving point, and the parameter is t here. And let me see, we can expand a bit that. Doesn't seem to be easy. Okay, and now you see the green parabola is a moving parabola, and as it rolls along the fixed parabola, the tip describes the red curve, which is the cissoid. Okay, that's fun. And you can have a the swing in the animation itself. Okay, let's stop here. And you see the key function here was that function here, arc, which is the arc of the parabola that I call CI1, which varies, and the range of variation of the parameter goes from pi, the origin, to u, which is the varying parameter. Now, shall give something similar for a surface, and that surface will be a knot defined with a so-called Viviane window. Maybe you don't remember what is a Viviane window. Viviane was a student of Galileo, and he remains famous in geometry for his window. And the Viviane's window is the intersection of a cylinder of revolution with a sphere. The cylinder passes through the center of the sphere, and it's tangent to the sphere. So this is defined here. And so you can see the sphere and the cylinder, and the green curve, which is dashed a little, is the Viviane window. Now, to form a knot from that curve, I define a cylinder with the function E cylinder here, which has as a base the Viviane window as for generators parallel to a vector which is -3, 0, 0. And it gives that. So you have the knot here. And the purpose now is to reconstruct the knot piece by piece. And the piece I shall choose is, you see, as it is a cylinder, there are segments. The generators are segments, and I shall reconstruct the knot with that segment. So in that case, the key function here is strip, and K is the knot that I defined before. And I may have two variables in that case, because in the general case, you have two parameters for a surface. But I just take one fixed, so the generator is fixed, but the one along the sphere, if you like, varies. So let's see what it does. So you can follow how it is built this way. Okay, like that. It's clear? And that is very helpful as soon as you have to investigate properties of curves or surfaces which are not too trivial, I would say. Now, a second aspect of interactivity which has been built up in GeometricaPlus is libraries of various elements. And the various elements are quadrics that I have quoted at the beginning, of parametric curves, because if you want to test things like the curvature, to be simple, of a curve, sometimes you want to have a sampling of all the things you can do, and there is a catalog of parametric curves in GeometricaPlus. Ruled surfaces and solids. So here, something is very important to notice. You can see that X here, let's say the command is very simple. It's quadric of X. But X is not an input parameter, it is an output parameter. And this is a bit counterintuitive, but nevertheless, it is the way it works, and it works well. So now, once you have this kind of catalog, you can select any quadric, in that case, either a paraboloid here or a hyperbolic paraboloid here. And if I put, for instance, is here, the draw 3D at pent of x. Oh, sorry. I shall give you a demonstration for the following. You can manipulate all that elements at will. I have an example here for the parametric curves. And here I took two curves. One I call CY, so I guess it is a cycloid. So let me find the cycloid here. It is here. And I define it. So I have here the parametric representation. And I shall take another curve that I call it TR, so that must be a trochoid, which is here. And you see, by giving a local name to the generic name Y of the database, I can manipulate the curves independently. For ruled surfaces, it is the same. Here, ruled surfaces are generated by lines which follow a certain variation. Here, what did I take? I don't know. Yes, I took a helicoid. So I'm looking for the helicoid. It is here. And I can manipulate it now, which consists of making a rotation. So by rotating the helicoid, I shall get a kind of aircraft helix. Hope. Let's say the parameter varies too much, but you have the flavor. So far, for the libraries, there is another kind of interactivity built in GeometricaPlus, which concerns the intersections. When you have curves which are complicated, the usual technique you would use with Mathematica would be to take a solver with an initial value, and once you have the initial value, you can solve precisely, but numerically, the two systems of equations, the system of two equations. Here, the definition of the approximate values is given for the two curves interactively, as I shall show you. And the function is dynamic intersections, excuse me. So I hope that you see it pretty well. Yeah. So the important function is dynamic intersections. So the first two arguments are the two curves that you want to study. And the third argument is the dynamic result of the intersection. So you will, in that case, it is a list of the parameters of each curve. So it will be the full list will be a list of two parameters at a time, one for the blue curve and one for the red curve. So let's see how it works. So here again, the output parameter is in the input string here. So this is a bit counterintuitive, but you will see it. You won't get used. So let me do the job. Excuse me, it's here. I take the slider. I have a slider for the blue curve, up, and I stop near this point. Excuse me, it's a bit too big because I not control of the second one. I have a second slider for the red curve. Okay, not too far. And I press solve. And shall reduce it again because you do not see it. Okay, you see it now. You have here the parameters of the two curves. Parameters are what they are, but we shall see afterwards. And I can continue for each point. Go here. I have to turn. Okay. Second point. Third point. Don't be afraid, it's a spiral, but I don't go to infinity. This one will go this way. Okay. Solve this third point, and I go to the last point. Here. Okay. Now I have the list of all my points. The very first thing to do is to check that the points you get are good. And to do that, you have two ways of checking your points: by looking at the points on the blue curve and looking at the points on the red curve. They should be the same. And to check that, there is a function which is called pointer, which associates a point bound to one of the curves. So I do that for the two curves. Excuse me, I have to do that first. Oh, that's technical, don't worry. And I let you judge that the result's pretty good. Okay? So you see, that proves that the technique is reliable. Now I can manipulate these points. Here, the manipulation I did just to give you a flavor of differential calculus. What I have done was I drew here the Freinet series system to see the tangent and the normal to each curve. Okay, it does not work for a strange reason, but it's like that. Okay, I'm sorry. But so you see, I finished there, unfortunately, on something which did not work as I expected. But you can be convinced, nevertheless, that this technique is very, very safe and rather easy to manipulate. And in conclusion, I would say that playing with this technique of interactivity for geometry has opened really new realms. And especially when you want to investigate complicated structures. And I think it's also something which could be generalized. I do here its suggestion, maybe in Mathematica, to have, for the time being, the dynamic applications in Mathematica are outside the code. It would be interesting to see a few applications inside the code. And I must finish by expressing my acknowledgements to Luc Barthollet, who suggested the syntax of these functions, especially something which was counterintuitive for me, to have the output in the input string. But it helps very much. Thank you.